Our first contribution deals with the proposal for an adaptive background subtraction algorithm for moving object isolation. Let us recall that moving object classification can be based either on image or on motion.
In image-based classification, each frame is scanned using a sliding window, and each window is classified. Recent approaches include semantic segmentation in order to classify regions of the data. In motion-based classification, only moving objects of the video are highlighted. This is done either using optical flow or background subtraction. Optical flow predicts motion vectors for each pixel in each frame. It has an advantage that can be applied even when the camera is moving. However, it is time-consuming. Background subtraction algorithms take as input a sequence of images and return as output binary masks where only moving objects are highlighted. Background subtraction are known to be fast. However, modeling the background implies that the camera is fixed or tempted to. In this work, we are interested in videos issued from static cameras, especially video surveillance videos. Hence, our contribution concerns background subtraction. Background subtraction algorithm combines two models: an adaptive Gaussian mixture model and an edge-based model. Our motivation behind using the original Gaussian mixture model is the multimodality of background, and our motivation behind proposing the adaptation of the original Gaussian mixture model is the variable number of backgrounds in videos. Our motivation behind using edges is that our aim is to extract a reasonable structured shape that will reflect the class of the object in the binary mask. The first step of our algorithm is the data preparation. Let us consider three frames. A buffer of three frames at time t is equal 1 to 2 and 3. Each frame is represented by its matrix, where the first two rows concern the red channel, second the green channel, and third the blue channel. Each pixel is represented by a temporal vector, where the first t values represent the red channel, second t values the green, and third t values are the blue. This is repeated for all pixels of the frame, which result in this case in 12 temporal vectors. The second step is the number of pixels selection. Here, each temporal vector constructed in the previous step is represented by a histogram in each channel. That histogram is represented by a Gaussian, where mu is the mean and sigma is the standard deviation. In order to explain how number of Gaussian is selected, let us consider two pixels with their temporal vectors. It is already clear from the first histogram that the first pixel is monomodal, while the second one is multimodal, especially in the third channel. The Gaussian distribution of the first pixel is given by a mean of 229 and standard deviation of 638, and for the second one, a mean of 210 and standard deviation of 30. In order to define number of Gaussians for the second pixel, we first extract peaks of the distribution. Then, for each combination of peaks K and L, we check if bins of the two peaks is greater than the threshold. If the bins themselves, K and L, are less than threshold, and if the distance between bin of the peak K and all remaining peaks of the distribution is less than threshold, and the peak K and all remaining peaks, the distance between them is greater than threshold, then the two peaks are chosen for splitting the distribution. The distribution is then split according to the mean of the two bins, which results in two new Gaussians. And we already see that from the new standard deviation of the new Gaussians is less than the original one.
Foreground is then extracted for each of the Gaussians with thresholding. To have the final mask, a pixel-wise multiplication of all resulting masks is applied. Edges are extracted using the trained random decision forest model proposed by Dollar and Zitnik in 2015. In the following, we do not give details about the training phase as it is described in the manuscript, but explain how edges are extracted. For each input frame, extract patches of size 32 times 32. For each pixel, get its 3 channel values in the CIE-LUV color space. Get its 2 normalized magnitudes of 2 scales, original and height-sized images. For each magnitude, get gradient orientation on 4 angles. Blur the patch with a 2-triangle filter and downsample by a factor of 2. Then downsample the image patch to 5 times 5 and compute pair difference for each pair and extract all previous features without sampling. The feature vector extracted has size 7228. Then, a mapping is applied to the feature vector in order to decide if the image patch is whether or not an edge. After extracting edges, using trained random forests described earlier, we apply a frame difference for each extracted edge. Since output of edge detector is an edge map, using a multi-Gaussian background resulted in a bad foreground extraction due to small differences between pixel values. Frame difference showed better results. The combination of the background extracted using adaptive Gaussian mixture model and the edge foreground is done using a simple matrix addition. Our validation in this step is only qualitative.
We can already see how edges of the contours of shapes is maintained. However, we can still see issues of split and merge in the shape. Observe in the first frame how the 2 pixels are moving separately, while in the second frame they are merged. Moreover, the feet of the second pixel is dissociated. In this step, we concluded that binary shapes issued from background subtraction can give reasonable information about objects and the class of the object.